If you think household chemicals were a 20th century invention, born with plastic bottles and bright labels, you'd be wrong. A medieval person lived inside a massive chemical workshop. They had no word for pH or a periodic table, but possessed sharp observation and an intuitive grasp of processes. The Middle Ages was an age of pure pragmatists, people who knew how to make substances work, turning ash into a cleaner, waste into a resource, and daily chores into sustainable, closed-loop technologies. Today, we're looking at the engineering of everyday life. How did the engineering of cleanliness actually work in an ordinary home? What did they use to wash clothes and scrub dishes? Why did these methods work? And what made their genius so dangerously clever? Let's start with the absolute foundation, the universal solvent that did it all, from laundry detergent to stain remover. Lye, the universal medieval solvent. In the Middle Ages, wood ash wasn't trash. It was a strategic resource. Burning wood leaves behind ash rich in potassium carbonate, the very same compound that's the basis for many industrial detergents we use today. People built real filtration systems, a layer of ash, then straw, then sand. They'd pour water through this makeshift filter, producing a clear, harmless-looking but powerful alkaline solution, lye. The most amazing part? Quality control. No instruments, no scales, no sensors. They'd test the concentration with a simple chicken egg. If the egg floated, the solution was dense enough to bleach linen. If it sank, they'd need to add more ash. It was a homemade hydrometer, measuring liquid density on the spot to ensure the perfect strength. Lye didn't just wash. It triggered saponification. Body oils and grease on the fabric turned into soap, right there in the water. The dirt wasn't just rinsed away. It was chemically transformed. This universal solvent was far from safe. Lye could eat through skin, cause chemical burns, and if you used too much, it would destroy the fabric. Getting the concentration wrong turned your linen into brittle, useless rags. Washing was brutally hard and genuinely risky. Laundresses' hands were often covered in cracks and sores, and the whole process demanded an incredibly precise sense of balance. You couldn't just make lye, you had to know how to control it, or its usefulness would instantly turn against you. But there was one problem even lye couldn't quite handle: stubborn yellowing and really tough stains. And for that, they turned to a form of chemistry we'd now call extreme. Ammonia, the secret history of liquid gold. For truly stubborn, deep stains, they turned to a resource they had in abundance: vats of aged, fermented urine. It sounds shocking, but chemically it was perfectly rational. As urine decomposes, urea breaks down into ammonia, a powerful alkaline compound. This wasn't haphazard. In medieval cities, urine collection was organized. There were special barrels and collection pits, and some towns even had municipal rules governing it all. People would sell their urine to launderers, tanners, and cloth fullers. They might get paid for it, or you might have to pay a fee to place a collection barrel. It wasn't a tax in our sense, but a recognized urban commodity with real economic value. Ammonia is great at breaking down fats and also helped to bleach linen. After an ammonia soak, the laundry was rinsed thoroughly in a stream and then spread out in sunny meadows. That's where the next ingredient came in: sunlight. Ultraviolet light accelerated the oxidation, finishing the bleaching process. It was a carefully designed technological chain: ammonia, water, and solar radiation. No chemical formulas, but a dead-on understanding of the process. While ammonia washed out of fabric, cleaning dishes was different. The enemy was the very nature of the metal itself. Scouring metal, chemistry without soap. Most kitchenware was made of copper and iron, metals that love to oxidize. Without regular care, they'd quickly develop a toxic, greenish coating. Their solution was a combination of abrasion and chemistry. They used a paste of fine sand, ash, and wine, tartar, the crusty deposit from wine barrels. This wine tartar is a remarkably mild acid, perfectly suited for dissolving stubborn metal oxides. The sand would scrub off the film, the acid would dissolve what was left, and the ash would neutralize any leftover acid, preventing more rust. It was a dance between mechanical force and chemical reaction. To protect copper, they used tinning, coating the surface with a thin layer of tin. Traveling tinsmiths would visit homes regularly to renew this protective layer. It was an early form of protective coating, the medieval ancestor of non-stick pans. But even perfectly clean metal and protected dishes didn't solve the biggest problem. The real threat wasn't on surfaces, but in the very air inside the home, in the atmosphere they were breathing. Medieval fumigation and chemical warfare. A medieval home was a perfect breeding ground for insects, mold, and fungus. Heat, organic matter, moisture, everything life needs to thrive. But instead of endlessly fighting the symptoms, they took an engineering approach. They made the living environment itself chemically hostile. The first line of defense: herbs. Floors were strewn with rushes mixed with lavender, wormwood, tansy, and rue. We often think of these as being just primitive air fresheners, but it was actually a form of fumigation. As people walked on them, the stems would break, releasing essential oils rich in terpenes and ketones. These compounds acted as natural insecticides, disrupting the nervous systems of fleas, lice, and other pests. It was a slow, constant, low-grade chemical assault. The second line of defense was the walls themselves. Whitewashing with slaked lime wasn't just about aesthetics. Calcium hydroxide creates an intensely alkaline environment with a pH around 12. Any organics, fungal spores, bacteria, insect eggs would suffer a chemical burn on contact with that surface. As it dried, the lime would steadily absorb CO2 from the surrounding air and turn into solid calcium carbonate, effectively sealing the walls. They even protected their food stores with chemistry, albeit a dry kind. Grain in the barn was mixed with a fine dust of wood ash or chalk. These microscopic abrasive particles would scratch the waxy coating on weevils. Through those tiny cracks, the insects would quickly lose moisture and die of dehydration. No poison, pure, brilliant mechanophysics. And then, the heavy artillery. If mold appeared in the cellar or pantry, out came the sulfur. They'd simply burn it in a sealed room. The acrid smoke was genuinely lethal. Hitting the damp air, it would turn into a suffocating cloud that would scorch everything living, from mold on the walls to rats and insects hiding within. It was crude, dangerous, but undeniably effective. Chemical disinfection, centuries before any lab standards. Medieval people had no word for microbe. Unable to see the enemy, they simply changed the environment so they couldn't survive. Even a perfectly disinfected home was useless without one last crucial element: controlled light. The engineering of light: tallow versus beeswax. Your light source depended on your wealth. The poor used a simple splinter of resinous wood that burned bright but left thick black smoke. The middle class used tallow candles. The cleanest and most expensive were beeswax candles. These were for the nobility and monks in monasteries, where light use was strictly regulated. Monastic rules would detail exactly how many candles could be used and at what hours. Wise. Light was an incredibly precious resource. Wasting it wasn't just seen as being careless, it was strictly regarded as a serious breach of discipline. Tallow candles required rendering the animal fat multiple times to remove proteins and connective tissues. The purer the resulting fat, the cleaner and more stable the burn. Even the wick was part of the engineering. You'd trim it regularly to control its length, and with it, the flame's temperature. A wick that was too long would cause the melted fat to evaporate much faster than it could actually burn, creating a thick, greasy soot. Light wasn't just a source of illumination, it was a carefully managed combustion process. All these technologies, washing, cleaning, lighting, they all came together in one place, in the air of the home itself. The zero-waste medieval ecosystem. You can't think of the medieval home as just a place to live. It was a closed-loop technological system, a mini-factory where every process was interconnected. Ash from the hearth wasn't thrown out. It was used to make lye for washing and cleaning. Leftover animal fat became fuel for candles. Wine sediment and acidic scraps were used to clean metal. Even smoke and soot played a role, influencing how the hearth and ventilation were designed. This created a closed cycle of materials where the very concept of garbage barely existed. Every byproduct had a potential use. This was empirical, zero-waste chemistry, built not on textbook formulas, but on generations of careful observation. Medieval people weren't aiming for sterility, but for control over reactions, smells, fire, moisture, and decay. Their life was a constant balance between benefit and immense risk. Yes, these methods were harsh and often dangerous, but given the resources they had, they were engineering masterpieces. This isn't a story of a dirty past. It's about how people without formal chemistry built a sophisticated, sustainable system right inside their homes. Today, we buy ready-made solutions at the store, rarely thinking that behind every bottle lie centuries of trial and error. We don't smell of lye anymore, but we still rely on the same principles of acidity and chemical reactions as those living under thatched roofs. So, which of these medieval household processes struck you as most ingenious? Do we do anything today that seems less clever? Let us know in the comments. And don't forget to subscribe. There's plenty more fascinating history to uncover.